have a car that is at the top of a hill, and that car has an initial speed of 10 meters per second, and I want to find the speed of the car when it's three-quarters of the way down the hill, and the hill has a height of 10 meters. What would I do? How would I solve this question? EI is equal to EF, right. What kind of energy does this car have at the top of the hill? It has potential energy, mgh. What else does it have? Or does it have anything else? It has kinetic energy as well because it's moving. Good. What would the initial height be? 10 meters, right? Okay, what kind of energy does it have at the end of this problem, which is three-quarters of the way down this hill? It's got kinetic and potential energy as well. Potential energy because it still has a height, and it's got kinetic energy because it's moving. Now, is final speed greater or smaller than the initial speed? Greater, right. The initial height was 10 meters, right? What's the final height going to be if we've gone three-quarters of the way down the hill? 2.5. We could solve for whatever we're looking for. Typically, that would be the final speed there. If we have a situation like this now, yesterday I drew it as if the charged particle was going vertical. But it doesn't have to be vertical, right? Because the electric field can point whichever way. Gravity always points down. The electric field can point whichever way. We'll make this one a negative plate. We'll make this one a positive plate. We'll put a negative particle right there going with an initial speed to the right of, let's say, 10 to the 4 meters per second. And let's say the potential difference across these plates is 10 volts. And let's say I want to find the speed when it reaches a point three-quarters of the way across. This is like a car going down a hill, isn't it? This charged particle, this electron or whatever it is going to speed up. It's repelled from the negative plate. It's attracted to the positive plate. It's going to speed up, just as the car in the first diagram speeds up as it goes down the hill. So how do we solve this one? Well, once again, we're going to say EI is equal to EF. What kind of energy do we have at the beginning of this problem? When this car, or this negatively charged particle, is at the top of the hill, before it accelerates. Does it have potential energy? Yeah, it does. But it's not mgh potential energy, it's QV potential energy. Be careful there about two things. One, this is Q big V, that is electric potential, the energy per coulomb. Okay, Q times big V, not Q times little v. And there's another equation that we've used, Q times E. People sometimes get those two mixed up. Q times E is electric force. Q times V is electric potential energy. Does that make sense? You can get those on your data sheet, right? You can rearrange the equation for electric force and electric potential energy from your data sheet. Just be careful though, because sometimes we have this tendency of skipping looking at our data sheet and just trying to remember it, right? Q times V, it rhymes with Q times E. Sometimes people just put Q times E in there instead of Q times V. So we do have an initial electric potential energy. We also have a kinetic energy because it's initially moving. Three-quarters of the way across these plates, does it still have potential energy? Yes. Does it have more or less potential energy than it had before? It has less, because this is like the car going down the hill. You're three-quarters of the way down the hill, you've got less potential energy than you started with, right? Does it still have kinetic energy? Yeah, in fact, it has more kinetic energy than it started with, right? Because this charged particle is speeding up. What was the initial potential there? 10 volts. What was the final potential if it's gone three-quarters of the way across? 2.5 volts. So we're saying here that volts, or electric potential, is analogous to height. If you've gone three-quarters of the way down the hill, your height is 2.5 meters now. If you've gone three-quarters of the way across the potential difference, or three-quarters of the way across the plates, then your new potential is 2.5 volts. Does that make sense? What kind of energy in both cases here, what kind of energy do we lose? What kind of energy decreases? Potential energy, right? Whether it's electric potential energy or gravitational potential energy, depends upon the context there. What kind of energy in both cases do we gain? Kinetic energy. So it's a conversion of potential energy to kinetic energy. And what type of energy doesn't change at all in both cases? The total energy. The total energy is kinetic energy plus potential energy. Now let's take a look at another one here. This time, let's say this car is at the bottom of a hill with a certain speed. Let's make it 10 meters per second. Okay, let's say that it goes up this hill, and we want to find out how high does it go? Okay, how high does it go before it comes to a stop at the top of the hill? Okay, this is a conservation of energy problem as well, but this time the car is slowing down. It's going up the hill. What kind of energy does the car have at the bottom of the hill with a speed before it goes up the hill? It's got kinetic energy, 1/2 mv squared. Does it have potential? No. What about when it reaches the top of this hill? Or when it reaches, not necessarily the top of the hill, but as high up the hill as it will go before it comes to a stop? It's got potential energy at that point, right? When it reaches its max height, does it have a speed? So it doesn't have kinetic energy at that point, right? Well, what about this? Okay, let's do a diagonal thing this time. Okay, this is a positive plate, this is a negative plate. Let's say that this is a positive particle right here, initially going at 10 to the 4 meters per second. What's going to happen to that positive particle? It's moving away from the negative, right? Because it was given, for whatever reason, it was given this initial velocity away from the negative. What's going to happen to it? It's going to slow down. It's attracted back towards where it was coming from. If it's going to slow down, then that's like a car going up a hill. So we're going to say, once again, just like the car going up the hill was represented by EI equals EF, we're going to say this charged particle slowing down is EI equals EF. What kind of energy does it have at the beginning there? Kinetic energy, 1/2 mvi squared. Now, remember, the electric field goes from positive to negative here, right? This positive particle experiences a force in which direction? I'm positive the force is with the field. So that means if it's moving kind of this way, then it's going to experience a force this way, and it's going to slow down. If it slows down, it's like the car going up the hill. If it's like the car going up the hill, it's kinetic energy being converted to potential energy. But it's not potential energy gravitational this time, it's potential energy electric this time. Q times big V as opposed to Q times little v, or Q times E. All right, what kind of energy do we lose in this case? What kind of energy decreases here? Kinetic energy decreases, right? What kind of energy do we gain, or what kind of energy increases? Potential energy, whether it be gravitational potential energy or electric potential energy. And what kind doesn't change? The total energy doesn't change, because the law of conservation of energy says its total energy remains the same. So we have a conversion when the car goes down a hill, or when the charged particle speeds up, of potential to kinetic energy. We have a conversion when the charged particle slows down, or when the car goes up the hill. We have a conversion of kinetic energy to potential energy. But in both cases, the total energy remains the same. Right? Let's take a look now at worksheet number 9 that we had for homework. Specifically, we're going to look at questions 4, 5, and 7. 4 says a proton is accelerated from a speed of 5 times 10 to the 4 to 5 times 10 to the 6 meters per second. What potential difference is required to do this? This is a charged particle speeding up, right? That's like what? That's like a car doing what? It's like a car going down a hill. If a car is going down a hill, then it's got initially potential energy, right? MGH. Although we're not going to write MGH, right? We're going to write QV. Now, if that car is moving at the top of the hill, it also has what? Kinetic energy. So we're going to say QV plus 1/2 mvi squared. Big V, little v. Now, at the end of this problem, what kind of energy does it have? Kinetic energy. So we're going to say 1/2 mvf squared. We sub in our numbers here and see what happens here. We're going to say 1.6 times 10 to the negative 19 coulombs for the charge. This is a proton, so it's positive. But even if it was an electron, we'd drop the sign of the charge, right? Because we always do that when we sub it into an equation. VI here, this is what we're looking for. Plus 1/2, the mass of the proton is 1.67 times 10 to the minus 27 times VI is 5 times 10 to the 4 squared equals 1/2 of 5 times 10 to the 6 squared. So what I want you to do is get this number, take this number over to the other side by subtracting, and then divide by 1.6 times 10 to the minus 19. And that gives me a VI, an initial potential of 1.30 times 10 to the 5 volts. Does that make sense? Now, strictly speaking, I was looking for the potential difference. What did I find? The initial potential. But the final potential is 0. The initial potential is 1.3. Then the potential difference will be 1.3, right? We don't worry about a negative or anything there. Now, this probably doesn't bother you because you probably never even occurred to you. But the reality is, it doesn't actually say here when it's 5.0 times 10 to the 6 at the end of it that the potential is 0, right? We made the potential 0 there. That's okay. Okay, just like on one of those conservation of energy problems on a hill, we can make the 0 point wherever we want as long as we're consistent through the problem. So what we're saying here is that we decided that the final potential was 0. Then the initial potential is just measured relative to the final potential. Does that make sense? Just make the final potential 0. Or in another question, make the initial potential 0, whatever works for you there. Okay, good? What if the question had said not what potential difference is required to accomplish this, but the question said what is the potential energy required to accomplish this? I'll give you a little hint. It doesn't make it harder. In fact, it makes it a little bit easier. If it said, what is the potential energy required to accomplish this? Remember the difference between potential, which is energy per coulomb, potential difference, which is energy per coulomb change, and potential energy, which is just energy. What's the potential energy required to do this? What would you do? No? Yeah. So?
So you just use that.
So multiply that by V, or by Q, I mean? Yeah, that'll work. So you could get the initial potential here, the potential difference is what it amounts to, and then multiply it by Q, and that's going to give you the potential energy, right? But I'll tell you what, there's an easy way of doing it. Why don't we just say this? If we're looking for the initial potential, instead of saying QV, why don't we just say EP? Right? Does that make sense? The initial potential energy plus the initial kinetic energy equals 1/2 mv squared. And why don't we just solve for EP here right away? Does that make sense? Your way works. It just means more work. That's all. Right? Okay, let's take a look at number 5 here. 5 says the potential difference of 100 volts exists between two parallel plates that are 16 centimeters apart. An electron begins at rest at one of the plates, accelerates toward the second plate. How fast is the electron moving when it's going on 4 centimeters, 8 centimeters, and 16 centimeters? There's 3 questions here, but I think if we do like 1 or 2 of them, I think we'll be okay. Okay, I think you'll get the idea for this one, okay? Let's do the first one. How fast is it moving when it's gone 4 centimeters? The electron accelerates toward the second plate. The electron is speeding up. That's like a car doing what? Car going down a hill. And when a car is going down a hill, we say EI is equal to EF. Now, picture this. The car is at rest at the top of a hill. Does it have kinetic energy, Matthew? When the car is at rest at the top of the hill, does it have kinetic? No. Does it have potential when the car is at rest at the top of the hill? Yes, but it's not MGH potential here, right? It's QV potential, right? Okay, well, what do we got? What do we got on the other side? What do we got when we've gone 4 centimeters across these plates? Is it moving now? Absolutely. It's sped up, it's moving. So we've got kinetic energy. Does it still have potential? Yeah, it's still got another 12 centimeters to go, right? It's only a quarter of the way down the hill. So absolutely, we're going to say QVF. All right, let's sub some numbers in here. This is an electron, 1.6 times 10 to the minus 19. What's my initial potential here? It's going to be 100 volts. My mass here is 9.11 times 10 to the minus 31 times VF squared plus 1.6 times 10 to the minus 19. What's my final potential? 75. Because I've gone 1/4 of the way across. I never sub the distance between the plates or the distance it's traveled into one of these conservation of energy problems. I just use that to determine what the new potential will be, or the final potential will be. Okay, so what I want you to do is get this side, get this, take this over by subtracting, and then multiply it by 2, divide by 9.11, and then finally square root it, and we should get a number there. The final potential of 2.96 times 10 to the 6 meters per second. Hey, it's faster than it started, right? It was at rest. Now it's moving at 10 to the 6. Seems reasonable. Okay? Now, did anybody spot for this question just a little bit of a shortcut? Anybody do it a little bit differently? No? Well, remember I said just a few minutes ago in the last question, you can really define your 0 point wherever you want? We could have done that here. We could have said, for this one, EI is equal to EF. We could have said initial potential, no initial kinetic, right, equals, well, let's define our 0 point when it's gone 4 centimeters. Does that make sense? I'm defining that as like ground level. Okay, if I do that, then what would my initial potential be relative to the final? 25. What do you think we get when we do that? Of course we're going to get the same answer, right? You can define your 0 point for height in one of those roller coaster problems wherever you want. You can do the same thing for potential here, wherever you want. This is a little bit shorter doing it the green way there, but I don't know that it's necessarily better. Okay? Sometimes, like in this question, question number 4, like we're gonna define the final potential as 0. It just makes sense to do that. In a question like this, you know what, it makes sense both ways. Whatever way makes more sense to you is the way that you should do it. Okay? If you want to save a little bit of time and it makes sense, do it the green way. But if you do it the blue way, it's not like it's going to take, an hour more. And you have an hour more for this exam anyways, right? You have pretty much all the time you need for your diploma exam. Question 7. This is a good question. I like this one. An electron enters the gap between parallel plates with a potential difference of 20 volts and 10 centimeters apart at 6 times 10 to the 6. How fast is the electron moving when it reaches the second plate if it's moving from negative to positive, and then if it's moving from positive to negative? I'm going to draw a picture here, okay? Because there's too much going on in this. I think it's useful to draw that picture here. Here's my parallel plates. Let's say that the electron enters those parallel plates at a speed of 6.0 times 10 to the 6 meters per second. The potential difference between the plates is 20 volts, which, what does that mean? The initial potential is 20 and the final potential is 0? Maybe it's 25 and 5. But it doesn't really matter, right? Let's define the final potential as 0 and the initial potential as 20. That's the easiest way to do it, right? But if you for whatever reason wanted to define the final potential as 13.5, that would be okay. You just have to make the initial potential 33.5, 20 more than the final potential. Okay? Makes sense, obviously, in this case, I think, to go 20 and 0, though. What else we got? The distance is 10 centimeters, although the distance apart here is irrelevant because it's going all the way across the gap in both cases. So it doesn't matter what that distance is. Okay, let's say in the first case it's going from negative to positive. Okay, this is question A. When it's going from negative to positive, is it going to speed up or slow down? It's going to speed up. It's repelled from the negative plate. It's attracted to the positive plate. So let's say for question A, speeds up, EI equals EF. Starts with potential, car at the top of the hill, speeding up, going down the hill, starts with potential. Starts at rest. No, it doesn't start at rest. Starts with the kinetic energy, so the car at the top of the hill is moving. We want to know how fast it's moving when it reaches the other side. So we're going to say 1.6 times 10 to the minus 19 times VI is, we're going to make it 20 because we're defining the final potential as 0, plus 1/2 of negative, of 9.11 times 10 to the negative 31 times 6 times 10 to the 6 squared. So get this number, add them together, multiply by 2, divide by 9.11, and then square root it, and you're going to end up with a VF of 6.56 times 10 to the 6 meters per second. That makes sense, right? Because it's faster. We said it was speeding up. The final speed is faster than the initial speed. Make sense? What if the question didn't say, what's the final speed? What if it said, what's the final kinetic energy? How would you change this? How would you make it easier if it said, what's the final kinetic energy as opposed to what's the final speed? Jack? Yeah. I mean, you could find the final speed and then say 1/2 mv squared, but the easier way to do that would just be to say, there's the final kinetic energy, right? Okay, question B. This time, the charged particle is going from the positive plate to the negative plate. What's going to happen to it now? It's going to slow down. It's attracted back towards where it came from. The electric field here goes from left to right. The negative particle experiences a force opposite to the field, which means it's going to slow down. And if it slows down, that's like a car going up a hill. And a car going up a hill starts off with what kind of energy? Well, better have kinetic energy, or otherwise it's not going to go up the hill. When it goes up the hill, kinetic energy, that's right. When it goes up the hill, still moving, it says, right? How fast is it moving when it gets to the top of the hill? Still got kinetic energy, although we would expect it to be less. But now it's got potential as well. Car at the top of the hill has mgh potential energy. So we sub our numbers in here, solving for speed there. Okay, get this number, take it over by subtracting. Multiply by 2, divide by 9.11, square root, and that should give us 5.38 times 10 to the 6 meters per second. Reasonable number? Started at 6. When it sped up, it went 6.56. When it slowed down, it went 5.38. Seem reasonable? Yeah, it seems entirely reasonable. Doesn't mean we're right. Okay, but there's no red flags to tell us that we're wrong.